Okay, in this video, we're going to be a little more formal. So far, we've had an introduction, we've seen a couple of examples, but we haven't really talked about Big O in formal terms. We haven't seen some graphs or any scary texts, so something must be wrong. So let's do that now. But before we do that, let's start with talking about what Big O actually is. Big O is simply used to formalize counting. It basically allows us to express how the runtime of an algorithm grows with the input. It allows us to describe the relation between the input to some function and the runtime of that function, how growing that input affects the runtime of our algorithm. Now, let's see some scary text. We can say that an algorithm is big O of f of n if the number of operations is less than the constant multiple of f of n as n grows. I know, this just seems like gibberish, but bear with me. What this basically means is that we have options. We have options on how our runtime grows with the input. We have options on how we can represent this growth in our input using big O notation. So here we have a bunch of different scenarios on how our runtime grows with our input. If you haven't seen this notation, by the way, where I say f of n equals something, this basically just described the relation between the input and the runtime, meaning that, say we have a function with an input n, so this one over here, and the output is the runtime. You can also think of it as the relation between the input and the number of operations. So this relation can, for example, be linear, as we see in our first example. Our function takes in n as input, and as that input scales, the runtime scales as well. The number of operations needed to run scales as well. It could maybe be quadratic, meaning that as our input n grows, the runtime squares. It could be constant, meaning that as our input grows, it doesn't really matter because runtime is always constant, which we simplify down to 1. Or it could be something completely different, like some other examples that we'll see later in the course. Now, one thing that I'd like to note here is that Big O is only concerned with the worst case scenario, the upper bound. What that means is that, for example, a lot of algorithms, say they are quadratic, would exit midway before actually doing n power 2 operations. They would only do as much operations in the worst case scenario, which we should always consider. So let's take a look at an example. Constant complexity. In constant algorithms, the number of operations that our algorithm takes doesn't change as our input grows. So for example here, in this pseudocode, we receive a number as input to our function, and what this function does is that it calculates the sum of the numbers up to that given input n, using this formula that we will, by the way, use to solve a problem later on in the course, and I'll prove it mathematically. So one thing to note here, the number of operations will always be the same no matter how big n is. Now, this is of course not always the case when it comes to algorithm. This is just the best thing that ever happened to humanity, constant algorithms. Introducing linear complexity, which is represented by big O of n. Now, in case of linear complexity, our number of operations needed increase linearly with our input. As our input grows, the number of operations grow. Therefore, the runtime grows. So, for example, here we got a function that also sum up to whatever number n that you give it, say 4. However, this time we find the result in quite a different way. We do a loop starting from 0 till n, and we add up our current value step by step, 1 by 1. Eventually, that would give us the expected answer, which is 10. However, there is an important thing to note here. This is the fact that n can be anything. N can be 4, 5, 100, 1,000, 1,000,000. And as n increase, our number of iterations inside the loop increases. Our number of operations in general increase, and our operations actually increase linearly with n. It can have a relation of 10n, 20n, doesn't matter. At the end of the day, we'll just simplify it down to big O of n. Of course, we're going to talk more about simplifying big O expressions later, but what you should know now is that the point is that the number of operations increase linearly with n, with our input. So even though both of these algorithms do the exact same thing, they find the sum of elements up to a given number n. The way the result gets calculated in each one is totally different and leads to drastic changes in performance as n grows. For the constant algorithm, it won't matter what we input. We'll always do the same number of operations. For the linear algorithm, it does matter what we input, because as our input increase, our number of operations increase, hence our runtime increase. So let's see another linear example. Here we got a function called print twice, and all it does is that it has two loops. First one will print the elements up to n starting from 0, and the second one will print the elements starting from n till 0. Now, both of these loops have n iterations. Sure, one starts from 0 and the other starts from n, but at the end of the day, the number of iterations of both of these guys are n. You might think this means that this is actually big O of 2 multiplied by n, but remember, we only care about the big picture. So this function has a complexity of big O of n. And again, don't worry about this simplification part, we'll talk about it later in the next video. Now let's take a look at some polynomial complexity. So here we got a method called quadratic. So things are a little different here. We got a nested loop. So here our first loop runs n times, right? But that's not the interesting part. The interesting part is the fact that for each one of these n iterations that we have in our outer loop, the inner loop also runs n times. So for each iteration in our outer loop, which happens in total n times, we do another n operations in the inner loop. That means that we do n multiplied by n operations, or n squared. So our complexity would be big O of n squared. This is a significant difference, of course. That means that as our input grows, our runtime roughly grows at the rate of n squared. So our graph would look something like this. So here our x-axis represent our input n, and our y-axis represent the runtime. And as you can see, the relation here is not as smooth as the linear complexity, because we see that our runtime grows a lot faster than the linear algorithms, because it grows quadratically. Let's see another example, just to cement things. This is a similar example, but this time we got 3 loops. Our outermost loop, which runs n times. Then we got a nested loop that runs n times for each one of these iterations of the outermost loop. Then we got yet another nested loop that runs n times for each iteration in the first nested loop. And you would get tired even talking about it. So this is pretty bad, actually. That's because this means that the number of operations is roughly n multiplied by n multiplied by yet another n. So this is big O of n cubed, n to the power of 3. So as our input increase, our runtime increase by a rate of n cubed. In the next video, we're going to see how to simplify big O expressions. See you then.